because 0 is a 0 vector, so any vector you add with 0 come to U. So, right? So we have actually, this is U, right? This is U. U plus 0 is equal to U. Now, I can exchange the addition, the order, so by commutativity of vector addition. Okay? Right. Now, but this is equal to 0 since U from is a 0 vector. Right? So when this is a 0 vector, then U plus a 0 vector equal to U. So now establish that 0 prime equal to 0. Okay, so we're done. Finished. Okay. You have to be very careful because I use what I have, right? Exactly. No more, no less. So you have to be only no more, no less, okay? Just good enough. So that any questions about that? To see a proof like this one is just like push you into a cliff, right? One more step, you are falling down a deep valley. Okay? So you have to be very careful. No more and no less. Okay? Any questions? Alright, so you know 0 vector. So in a vector space, there is one and only one 0 vector. So we establish the uniqueness of 0 vector. The next thing is we want to establish the uniqueness of additive inverse for any vector. Theorem. Alright. So the next theorem is that in a vector space, each element U has one and only one additive inverse. Okay, so for each element, vector, there is one and only one additive inverse. Okay. All right. So we let fix a vector U B. So we let X and the Y be additive inverses of U. i.e. that X plus U equal to 0 and Y plus U equal to 0. Right? So suppose that we have for a certain vector U, we have two additive inverses, so that X plus U equals 0 vector and Y plus U equals 0. Okay, so that is the assumption. And we want to prove that X equals 1. This is what we want to prove. So we proceed this way. X is equal to X plus 0, right? zero element, that is the existence of zero vectors. That's what? Now, this time 0, I want to use 1. Okay? Plus u. Okay, because this property. Alright? And by also and by commutativity, I exchange the order. And then by associativity, and here x plus u is 0, so I have 0 plus 1. Okay, and I change the order, and this is equal to 1. Okay, so you may give the reason. For example, axiom, say 3. And here is from here. So I will say this is equation 1, alright? So this is 5. Equation 1, right? 1. And this is axiom 1. Here, commutativity. And this is the axiom 2. Associativity. And this is the axiom. No, this is from equation 1. And again, axiom 1. Okay, commutativity. And finally, axiom 3. All right. So now we know for any element, any vector u, then u has one and only one additive inverse. Next theorem. Well, so we have we may have a question. So in a vector space, 0 times u equal to the 0 vector. Okay, for all u. So we may ask, because the unitary property says that the scalar 1, right, the real number 1, multiplied with the vector is equal to the vector itself. But how about the 0? Because 0 is so unique, right? The real number 0 is very unique. So we may ask, what is the scalar multiplication of the scalar 0 with an arbitrary vector? And of course you say, oh, it should be the 0 vector. you guess that. You may guess that. This because it's quite natural, right? But you have to prove that. Even it's quite natural, you have to prove that. So here is the idea how to prove that. So again, we have all right. So 0u, all right, is equal to 0u plus 0, all right? Right. So because 0 times u is a vector, right? It's an arbitrary vector. Now by axiom 3, the property of 0 vector is this vector added with 0 vector will be the same. Now, so this is and we know this is we have u plus u, okay? Because u has inverse, right? So this inverse add with u is equal to 0. Now 0u and plus by the way 1u. Okay, so this is axiom 3. This is axiom 4. That is the inverse. This is axiom 7, right? Unitary property. Now I have u plus 1. I'm sorry. I forget. Actually, I have to. This axiom 1. I have to change order. I'm sorry. 1u. And so this is axiom 7. Okay. And so now 0u plus 1u plus 2. Okay, so this is associativity, axiom 2. Now 0 plus 1, so we use distributive law, so this is u. So this is axiom 5. And this is 1, u plus u. Okay? Right. And so that so this is u plus axiom 7 again, and u axiom 1 again, conductivity, and this is 0 vector. Okay, axiom 4. And we're done. So prove that 0 times u is equal to 2. But it's very detailed, but sometimes I can, for example, if we take commutativity of a vector dish as granted, then I just exchange it, right? So, and also the associativity is so trivial because we have associativity, so we can do that without mentioning the associativity. But anyway, it just give you the idea. So we solve the problem that the scalar 0, scalar multiplied with a vector come to the 0 vector. Okay, right. And so now we answer the question that can we have a more sensible notation for the additive inverse u cubed? So the theorem is that u cubed is equal to minus 1u for all u. This is quite natural. So we know from the theorem, we know that for any element, for any vector u, there's one and only one additive inverse. So we know u cubed is unique. We already know that. But what exactly u cubed? All right, and we can express u cubed, the additive inverse, by this expression. So it's actually is the minus 1. Minus 1 is a real number. Okay. The scalar multiplication with the vector u is. All right. So this is true. All right, and so that so we just check. We check that. All right. We check whether this is equal to 0. All right. So this is 1, right? By axiom 7. The unitary property. And now we have, by use distributive law, axiom 5. Later on, I will forget 1, 2, 3, 4, 5 because I'm a member maybe tomorrow. But I will know that this is distributive law. Okay, I will say, oh, by distributive law or something, but it's too lengthy, right? But at the moment, I think this is much more shorter. But so xm5 is distributive law here, but the addition is 0, 0u. Okay, it's 0. And we just prove 0u is 0. So this is 0. So we know that. So that's which is an additive inverse of u. Right? So we know minus multiplied with u is minus 1 multiplied with u is an additive inverse of u. But we just show that additive inverse is unique. So this one, single additive inverse is unique. We have right, so we're done. Okay. So that is the situation, okay? Alright, and another theorem is interesting is that alpha at 0 equals 0 for all alpha. This is another way to here. If you have an arbitrary real number, scale multiply with vector, then it becomes a real vector. I think that's Okay. And repeat a definition of a vector space. So, but we haven't finished yet the list of theories, which should be satisfied. So, a vector space actually is a set. First of all, it's a set of elements, and we will call these elements as vectors. Okay. If they satisfy all the things in the following, so set together with two algebraic operations here. So actually, there is a vector addition and a scalar multiplication. And for vector addition, actually is that for each pair of vectors. Okay, so I define the addition product way, so that this pair. Then we have the sum of chain manipulations, bringing them together so that it becomes another vector. Okay, and this vector will be denoted as the sum of U and V. Okay, so this is called vector addition. And also we have a scalar multiplication, so that pick up a real number and a vector here. Then with some operations, manipulation among these two objects, you get another vector, and this vector is represented by alpha 3. So here we have a multiplication, but we then it as a break here. Okay, so it's just it's just a custom that we write to scale multiplication this way. And so we have, and these two algebraic operations to satisfy our give a list of properties and we call accents here. Okay, so for example, for vector addition, we have commutativity. So you can you order the summand here. Okay, get the same result. And also we have associativity that if you sum, you want to sum three vectors together, you can do it first of all for the first two, get the sum, and then the result with the W, the third vector, get the sum. And the result will be the same as you do V and the W first, get the result, and sum with the U. So we have associativity, and also there's a very special element called zero vector. Okay, in the set V, and the zero vector is something that if you for any element or any vectors that if you act with this particular zero element, then you change nothing, so you get the U itself. Okay. And the first one is the existence of an additive inverse that says that for each vector U, okay, there is an element U cubed, such that the sum of U cubed and U becomes to the zero element. Okay, and so the zero element here is universal, means that this is true for all elements U here. But for the inverse, that the U cubed depends on U. Okay, different U may have different inverse here. Okay, so but the important thing is that the sum of U cubed and U will be equal to the zero element. The mentioned zero element here. All right, so this is all about the vector addition. But we have to mention some properties about the scalar multiplication and the interplay between the scalar multiplication and vector addition. Okay, so here is that we call it distributional. Alright, so distributive law. Okay, so that there are two versions. First version is that alpha u plus v equal to alpha u plus alpha v. Okay, and alpha plus beta u equal to alpha u plus beta u. Alright, so the scalar multiplication is distributed relative to the vector summation. Okay, so you can, so the thing is that you can, first of all, you get the sum of u and v and take the scalar multiplication with the scalar alpha. The result will be the same as, if you first take the scalar multiplication of alpha with u and the scalar multiplication of alpha with v, and add them together. The second version is about the scalar multiplication is distributed to the scalar additions. Because the scalar, we know the scalar is in the field of real numbers, that for a field that we can do addition, subtraction, multiplication, and division. Right? So for the addition of two scalars, the scalar multiplication will be distributed relative to the addition of the two scalars. And the sixth is about the play that associativity of scalar vector multiplication. Okay, so meaning is that because that for scalars, we know we can multiply two scalars, right? So alpha and beta and u. Oh, I have to say for all. Okay. All right. So you can do the scalar multiplication first. I'm sorry, you can do the product of two scalars and then get the scalar multiplication. Or you can do it the beta multiplied with u and then take another scalar multiplication. So for here, you do two times of scalar multiplication. Do two times. But here, you do one multiplication of two scalars and one scalar multiplication. So they are different. But the result will be the same. Okay, so it's called associativity of scalar multiplication. And seventh thing is that we call neutral property. It says that 1 and the u equal to u for all u. The scalar 1 is a very special role. If you do the scalar multiplication between the 1 in the real number and with a vector, then you will not change it. It's called a unitary property. Very special kind of property you have. Okay, so I just did 7 because I combine the two kind of distributive law together. Make it simpler. All right. So this is the vector space. And vector space play the most important role in this course, linear algebra. So you have to be and ask you to become to be a good friend of vector space. All right. So now I will examine some of the theorems which can be deduced from all these axioms. Okay. So first of all, the zero vector. So maybe I will speak in the way. Let me see what kind of way I can speak up. Say okay. So maybe I in a vector space there exists one and only one zero vector. Okay, so the existence of a zero vector is stated here. It just says there is a zero vector, and the question is zero vector unique? So this, can we have another zero vector different vector that has the same property? Okay, so the theorem states that no, there is only one, no other. So zero vector is initial. All right. So to prove that, so we say let 0 and 2 0 vectors in V. So set 0 and 0 prime satisfy here as well as here. Anyway. All right. So now we can. So we have so now 0 prime. Okay. 0 prime is 0 prime plus 0. Okay. By axiom 3, maybe I will say axiom 3. Since 0, that is intuitive, right? So, but we have to prove that. So the proof it is like here is that alpha 0, all right? So alpha 0 actually it's alpha 0 plus 0. Okay? Because 0 is equal to 0 plus 0. By axiom 3. Because 0 itself is u, right? It's a vector. So a vector head with the 0 vector is also equal to the that vector itself. And by distributive law, so this is axiom 5. Okay, up to now. Now you add okay. So now on both sides you add minus 1 times alpha 0. Okay, and we know that this is 0, right? Because this is the inverse of this vector, so this is 0 vector. And here, and we do the associativity, so we have that. Okay, and this is alpha. And we have that. Okay. So so my case a little bit faster than before. Okay. Is that okay for you? So here I just add this vector on both sides, and then maybe you will think I'm too fast. Maybe I write here. Originally, when I add them, I have to put the parentheses here, and then I use associativity. Okay, this is a cross associativity here, and this is 0, right? And this is 0. Here 0, alpha 0, and we change the order. And well, anyway, but if you implicitly applying the conductivity, then you can just write 0, write alpha 0 here. Okay, so this is quite obviously that we have that. So so the final interesting thing is that if alpha u equal to 0, then now so suppose we have a scalar alpha and a vector u such that the scale multiplication get you the 0 vector, then either alpha equal to 0 or u equal to 0. Okay? So that means that if alpha is a non-zero scalar, u is a non-zero vector, then the multiplication should be non-zero vector. That is the implication. So proof. If alpha equals to 0, we have done. Okay? But if alpha equals to 0, we have done. No problem. Because alpha is 0, 0 times root is 0. We proved that before, right? Yeah. But now, if alpha not equal to 0, if alpha not equal to 0, then we multiply the inverse of alpha, multiply 0 here. What is that? Use the theorem. This is 0. Okay. And now we go forward. So now times alpha equals to 0. Right? We use the associativity for scale multiplication, and this is 1. Okay? And by unitary property, this is 0. And we have done. So if alpha is 0, fine. We just done. But if alpha is not equal to 0, then u must be 0. Okay, so there are so many. So there are some simple properties we have. Any questions? Yes, please.
那个右下角那边正就是两边同时加一个负阿尔法，就是你两边同时加一个东西，这样证明下来没有证明到，就是没有证明说两边加同样的东西，然后是有什么东西。就比如说像正 A 等于 B， 如果两边同对率，然后再证明这一点就没有意义。我们没有证到那个叫什么？就是两边同时加一个东西，它会是什么东西？所以这样证到吗？就是。
Well, I just use that if I have two vectors, suppose I know x and y are equal, right? Then I just add another vector will be equal. Because the mapping, vector addition is unique, right? Mapping is, you should have a unique value. So if this is true, then this must be true, right?
就是 那个加法是要是
Because I use vector addition, and we define vector addition in the vector space. So it's just like a, it's just like a, let me, this is the function value, right? Because plus is a function. We apply the plus function on the pair of vectors. So the value, we use this sum as the value of the function. Is that okay? Because plus vector addition is a function. It makes a pair of vector into a vector, a pair of vector into a vector. Just like suppose if V is R3, okay, and vector addition is that you put say U1, U2, U3, U1, U2, U3, right? So you make them equal to U1 plus V1, U2 plus V2, U3 plus V3. Okay, it's a vector here. And we denote this vector as U plus Q. Okay. So the addition is defined by component-wise addition. Right. So plus the operation, the vector addition actually is a binary operation. So it's a mapping. So every time you get a pair of vectors, after the addition, the sum of this vector is another vector that we call the sum. So t plus x actually is a function, the plus function offered on the pair. But because x equals to y, so I can replace y by x. Just a simple, right? Because I use two simple to denote the same thing. Okay, and this is what is that? This is. So x equal to y implies z plus x equal to z plus y. Just like if I know a scalar variable, then 3 times x is equal to 3 times y. We know that because 3 is a non-zero scalar. But suppose suppose that we have two real numbers and we know they are equal. Okay? So that now then we have this one and we know 2 plus x. We are so familiar with the scalar multiplication, the multiplication between two scalars or the addition between two scalars. We are so familiar with that. So every time we just solve them in this way. Especially, xy can be very complicated because that I know the expression something like but I have two expressions and I say that they are equal. I want to know the relationship between x and y. How can I do so? Well, first of all, I can substitute 1, right? And when you question the identity,
不是对，那个我没有否定，我是说在那个空间是对的，就是这个东西不是那个加法，就是这个加法。
Yeah, but that is the vector addition. But I have defined that the vector addition is that. All right. The reason why I can do that is because that they are equivalent to each other. All right. Let me say x equals to y. You can only z plus x. So they are equivalent to each other for all z.
就 个东西不用证吗？就是
Oh yeah. Actually, if we, yes. Okay. This impression, this direction, I have done that already. Why? Because I just said the vector plus is equal to a function value. And so now I just use x equal to y, right? So I can replace x by y because they are the same vector. And so this is the definition of mapping, you know. You cannot deny because the vector addition is just whenever you take two vectors together, when you take two vectors as a pair, you can always add them together as a sum. This is the definition of the plus, the vector addition. This is the right definition of that. We assume this vector, this algebraic operation exists. I just assume that we have that function. I can show you later many different examples, but you should admit that it is a function operate on two arguments. And because that x equal to y, so I can replace x by y, right? And this value, what is that value? It's just z plus y. Because z plus y is the function value, is the expression for that function value. Okay. So the reason why I can get that because this implies this one. To go back, sure, I have to use what? Use the additive inverse. Right? I have to use additive inverse. So the direction is because that I have the vector addition operation. I know your point, but you can think about that. The really point is that when we push back to the bottom, it is that we have the vector addition. The existence of vector addition gives us the identity here. It's a very good question. Because you push back to the origin of the definition of vector space. So that is a very good question. So I could say it is here. Okay, and so that I can add them together. Okay, other questions? All right, so let's take the first example. So we consider such a set. So what is this set? It's the set of all polynomials. Of degree less than 2. Okay? Real polynomial means that the coefficient of polynomial are real numbers. So B is just a set of all real polynomials of degree less than equal to 3. And we know this is just a formula for such a polynomial. So we define we have a set. We have defined vector addition. Alright? So how we define them? Well, suppose we have so we do the traditional addition of two polynomials. But you can write it directly. So given a pair, we go to what? The addition is that go to another vector addition. So we go to a polynomial. Alright? So the vector addition is that when you add two polynomials, you really add the corresponding coefficients. Okay, so this is the addition. How about scalar multiplication? Alpha. Go to alpha A0, alpha A1, alpha A2, alpha A3, A3. Right, so you have a scalar multiplication defined by, so when you multiply a scalar with a vector, a polynomial of degree less than or equal to 3, you end up with a polynomial of degree less than or equal to 3. The only thing you change is the coefficient. Every coefficient of the original polynomial is multiplied with alpha. Right. So now you have so these two mappings, these two functions are well defined. Because I give you the rule how to get the sum. Here, this is the sum of these two vectors, and I give the rule how to get the scalar multiplication of a scalar alpha and a vector. So that's the rule, and you get it. And now you have to check the 7 axes. Okay. So you have to go through the 7 axioms in detail. But to save time, I just mentioned that because we are so familiar with the addition of two polynomials. We are familiar with the multiplication of a scalar with a polynomial. So you see that if you change these two polynomials, that means that you change the addition of scalars here. But the addition of two scalars is commutative, right? You can commute. You can change the order of the scalars so that the commutativity of vector addition is satisfied. And similarly for associativity, okay? Because it's corresponding to the associativity of scalars, additions. How about the zero vector? Well, that's zero polynomial, right? Zero polynomial is the 0 plus 0x plus 0x squared plus 0x cubed, right? So you have the zero polynomial give you the zero element. No problem, right? How about the additive inverse? Well, you just take the negative of the negative of every coefficient. So you get the inverse for each polynomial. So 1, 2, 3, 4, x and 1, 2, 3, 4 satisfied. How about distributive law? Well, we can check, right? So actually, I just checked the 7 axioms verbally. I write down everything here because if I write everything, I would take half an hour. So it's long. And how about the 7 axioms that unique properties? Well, if this is 1, right? How about 1? Then you will not change the coefficient. Because 1 times A0 is A0, 1 times A1 is Okay, so the unitary property satisfied automatically. So everything. So that so I just say we can check that all 7 axioms are fulfilled. That we okay, so now we know that the vector spaces of all the set of all real polynomials of degree less than 3 is a vector space. Okay, and very often we use P3 to denote this space. So P3. And so remark. Even the set of all real polynomials of degree less than equal to n is a vector space. Okay, so this is very common. One, two, and the P, the set of all real polynomials right? It's also a vector space. But when you write down the vector addition and schematification for that, then you have to very careful to know that. Here, when you write down the vector addition, okay, then you have to write right? So you have to write down these two polynomials may have different degree. Okay. In here, because I know the highest degree is 3, so when I write the definition, I can write it up to 3. Okay, and you have but for here, you have to write it this way, and so you go to that. So you have to write it as the sum. So it's a technique of writing down this middle location. So here I will use this. Right. So as we all practice, if you add two polynomials which may have different degrees, the result is that you have a polynomial with a degree which is the highest, right? The higher one. So you take the maximum of n and n here. And you get the AI plus BI and there's that. And then you will say that a convention with AI equal to 0 when I greater than n and the BI equal to 0 when I greater than n. Okay, so you just assume that because when you write down something, you have to say something for any new locations. So it's possible that probably the index I will beyond n. But in your definition, when you write down the polynomial, you only write up to an. You don't write an plus 1, an plus 2, no, right? So you have to give something back when you write down this notation. Right? And the scalar multiplication, then that is simple, right? The same. Okay? And then finally you can say for all n. Right? So that's it. So you can write down the definition of the vector addition and scalar multiplications. Then this is because you want to give a rule for vector addition, a rule for scalar multiplication. And when the vector space becomes more and more general, you have to know how to write it down mathematically. Okay, so we now start from the set of all real polynomials of equation 3. We know it is a vector space. We extended that it is true for Pn, and also it's true for P. P is the set of all real polynomials. All right, the second example is more interesting. So we let C the set of all real values continuous function. Defined on the first interval. Okay, so C means continuity, right? And this is the interval, the interval to define the real value function. Okay. So mathematically, we can think about that. This is alright. So it consists of functions defined on the first interval and its real value, such that continuous. Alright. This is another way to describe it. Alright, so vector addition. How to define two functions? The addition of two functions in this set. The result is just add the value together. Right? Scalar multiplication. Just multiply alpha to each value. So it's very simple. But the point is that by definition, because I want this function, of course this is a function from this interval to R. But the question is that if I have two continuous functions, is the sum of these two continuous functions still continuous? But the answer is yes from calculus, right? So this is well defined. So you have to check. Right? Even though you give a definition, you have to check its value. You have to check that the function value here is still in here. In calculus, so I have to say in calculus, the sum of two continuous functions function f of x means function, okay? Because I run out of my time. Because before you take the quiz, I want to give you 5 minutes break. So I have only 4 minutes left. Anyway, so in calculus, right, the sum of two continuous functions, right? Okay, functions is continuous, right? This is from calculus. So this one is in C. And also, if f of t is continuous, then when you multiply with the scalar, the new function here is also continuous. So you have to say that this is also true. Similarly, use f of t. Okay, so that the vector addition is well defined, the scale addition is also well defined. So that as the vector become more and more complicated, I would say to define vector addition, define scale multiplication become more and more complicated, and then you have to check whether the vector addition to define is well defined, and also you have to check the scale multiplication given is also well defined. Once you have done, now the others, the 7, so we can check that all 7 x's are fulfilled. Yes. C. Alright, I stop here, and we have a 5 minutes break.